So this is a quick review of the basics of UCM, or Uniform Centripetal Motion. So what is uniform centripetal motion? Well, the basics are right here. You got to have a constant radius as you go in a circle, and you've got to have a constant speed as you go in that circle. So here's our circle right here. So I'll move this out. So let's say we've got this little object here, little planet or a bug or whatever, and it's going around as best I could make it in this circle right here. So it has to go in a constant speed. So what are some of the things, if we were going to study this, that we would be interested in? Well, one of them clearly is the radius. So we'd want to know how big the radius is. And another thing we might want to know is how long it took to go around once. That time to go around once is called the period. The symbol for that is a capital T, and it's measured in seconds. We can think of it as the seconds per cycle. So how many seconds it takes for this thing to go around once, let's say. Cycle's not really a unit, it's just a count, so the unit's really seconds there. So imagine this thing took, 6 seconds to go around once. Then the period would be 6 seconds. By the way, in later units, it's going to be important to recognize that one revolution, one rotation, is the same thing as 360 degrees all the way around, which, using radians as our unit, is 2 pi radians. But we'll worry about that a little bit more later. Well, what if this thing was going around really fast? What if this thing was going around like 60 times per second? It was going so fast. Then the period would be quite small. So sometimes then we don't think of the period, we think of that and we take it and flip it on its head and we think of the frequency. So the frequency is not the seconds per cycle, but it's the cycles per second. Frequency, by the way, the symbol for it is lowercase f, and its units are cycles per second, but we've renamed that a hertz. The abbreviation for that is Hz. So if this thing went around 60 times per second, that would be a frequency of 60 hertz. Remember here, since it's seconds per cycle and cycles per second, they're the flip of each other. They're inverses. So if the period is 1 over the frequency, then the frequency is equal to 1 over the period there. So they're flipped. So if the frequency again is 60 hertz, then the period is 1/60th of a second. If it took 1/5 of a second to go around, then the frequency would be 5 hertz. So to find one or the other, you just flip them there. Another thing we might be interested in is the speed at which it goes around. Remember that speed is always distance over time. But we're going to be interested, let's say, in going around once. If we go around once, we go around the circumference. To find the circumference, that's 2 pi r. Well, we've just discussed the time to go around once is the period. So the velocity of something going in a circle is 2 pi r divided by the period. By the way, since dividing by the period, it's the same thing as multiplying by the frequency. So you don't see this used near as much, but it's the same thing. 2 pi r times the frequency is the same as 2 pi r divided by the period. Let's talk about this velocity a bit more. So let's say it's going around here clockwise like this. Up at the top, what way is its velocity pointing? It's pointing like that, straight to the right there. And then a little bit later, it's over here, and then its velocity is pointing down like that, tangent to the circle. And then it cycles around down here, and now the velocity is pointing like that, also tangent to the circle. Let me move it over a bit. And then we get up here, and now it's pointing like this, always tangent to the circle at any given moment. You can imagine the dot is at 1 around here. So sometimes we refer to the velocity of something going in a circle as the tangential velocity there. Notice we say, coming back to our definition for a second, that it has to have a constant speed. But because the velocity keeps changing the direction that it's pointing, and velocity is a vector, it cannot have a constant velocity. So its velocity is changing even though its speed is constant. So this thing is accelerating even though it has a constant speed. Because remember, to accelerate, you can speed up, slow down, or change directions. So what is the direction of this acceleration? Well, sometimes it's a little bit easier to picture the direction of the force. So if this thing is going around clockwise. It wants to go in a straight line. It wants to go over there, but we have to push it back. What way are we pushing it? That way. And again, let's say imagine it goes here. It wants to go, when it's right here, it wants to go this way in a straight line because of inertia. So we push it back. What way are we pushing? We're always pushing towards the center of the circle. So this is why we call it centripetal. So this word centripetal right here is Latin for center seeking. So, or you can think of towards the center. So when the ball is right here, let's say, in order to keep it in a circle and not go off in a straight line, we must push it, come back little ball, we must push it towards the center, always. If it's up here, we must push it this way, towards the center. So that is the root of the word centripetal. By the way, acceleration and forces are always in the same direction. So the acceleration will also point towards the center. If we're up here on top, then we have to push it down towards the center, and the acceleration will be down towards the center as well. So this picture kind of sums it up here. Here we have something going in a counterclockwise fashion. At this moment, the velocity, let's say, is tangent to the circle, that direction. Both the acceleration and force point towards the center. And note the A sub c and the F sub c for centripetal acceleration, towards the center, and centripetal force, center-seeking force. Sometime later we'll be over here, and at that moment our velocity is pointing this way, and you may think, oh, it's pointing almost opposite. A is pointing this way here and this way here, but the constant is always towards the center there. So what is the value of it? How do we find it if the velocity is not changing? Because normally we find velocity by doing the acceleration by doing the change in velocity over time. So there's a unique equation in this chapter. The centripetal acceleration is the velocity squared over r. Remember, this is constant. It doesn't have to change. So lots of times, not only will we find the centripetal acceleration, but remember from Newton's second law, force equals mass times acceleration. Net force, really, but we'll just call it force here. So just as often as you use this equation, you'll use this one. Centripetal force, then, is mass times centripetal acceleration. So it becomes mv squared over r. And these equations, these concepts that we just talked about there, are the heart of the centripetal motion and gravity unit.